Well, I did it again. I told you in this video we're going to be looking at another reaction, and this is alkene reacting with a halogen, but this time instead of methylene chloride and water, it's going to be an alcohol. All right, well, how do these things happen? What goes forward? Well, let's figure them out. I think that you can actually tell me already before I even explain this. All right, so let's say that we have CH3, CH double bond, C with a CH3 that points to the top and CH3 that points over here to the right. Very similar to what we've used before in the past, all right? And then we're going to react this with Cl2, but this time we're going to put it into the presence of an alcohol. And I'm just going to choose methanol, but any alcohol will work. It doesn't matter. They all work the same way. So the question is, what kind of product would be formed? Well, just like before, I'm going to start with my starting reagent, CH3, CH, double bond, carbon, with a CH3 that points up and a CH3 that points over here. And guess what I'm going to do? I'm going to break that double bond. Two sides of attachment open up, and chlorine goes on first. That's the electrophile, and it looks at these two carbons, and it says, I'm going to play with the other hydrogens. So chlorine decides that the carbon to the left has 1, the carbon to the right has none. So chlorine's going to go here. Then the other side of attachment, that's freed up. Chlorine could go there. That's not a problem. But that is the minor product. It doesn't happen a lot, and that's because we have a solvent. And that solvent in this case is not methylene chloride. That solvent in this case is not water, but that solvent is methanol. So think of this as HOH, right? And the OH part went on to the molecule. Well, the O and the R group piece goes onto the molecule here. This hydrogen, remember, is ripped off. It's either ripped off by another alcohol molecule that's there, or it's ripped off by the chlorine that was freed up from that twin of Cl2. So this hydrogen's no longer there at that point. That creates this OCH3 that will go on to the molecule. Folks, that is the addition of a halogen with alcohol. Now, if this was CH2, CH3, and we used ethanol instead, then it's still an OCH2, CH3 that gets added on down here. There's no difference in that. Whatever is attached to the O is going to get attached here. So that is the addition of a halogen with an alcohol. Now, what type of compound is formed here? Well, this is an R group, and this is an O and another R group. I see a carbon on both sides. So this is going to be regarded as an ether. So whenever we do a halogen, and an alcohol, we end up with ethers as products here. But they're halogenated ethers, meaning the longest carbon chain is here, 4 across. This is going to be a butane. I look at my ether group, I number closest to that side, so carbon 1, carbon 2, carbon 3, carbon 4. Carbon number 2, I see my ether piece. This is a 2-carbon chain and an oxygen. So we're going to call this ethoxy. So this is a 2-ethoxy butane. On carbon 2, we also have a methyl group. And on carbon 3, we have a chloro group. All right, so 3-chloro, because C comes first. Then we have an E and an M. So the E actually comes next. So 2-ethoxy. And then on carbon number 3, we have a methyl group. 3-chloro. No, sorry. Not on carbon 3. On carbon 2. 3-chloro, 2-ethoxy, 2-methyl butane. And folks, there's the name for the product that we've just generated. All right, one more example of this. Let's do CH3, CH, double bond, CH2. Just to keep it simple, we'll add bromine on because we used chlorine last time. And this time, let's do something like this. What goes on here? This is a salt. Folks, this is table salt. You put it in your spaghetti water. Okay, so I've got this alkene. I'm going to react it with the Br2, but then all of a sudden I'm bringing salt into the picture as well, and the answer is yeah. This salt can actually be added to the bromine or to the chlorine, and we can get different types of products that happen here. What do we get? Okay, well, this is what happens. Just like before, we learn a procedure and we apply it. So CH3, CH, double bond, CH2. So in all of the other cases, we the double bond, and then we open up two sites of attachment. That bromine initializes the reaction here, and that bromine acts like a hydrogen and it plays with other hydrogens. Markovnikov's rule is followed, just like before, just like always, no difference. So here we get a Br2, that Br comes in, and the Br says, I like this spot because there's more hydrogens and I like to hang out with those hydrogens, so that's where I'm going to go. See ya, bye-bye. And the other bromine goes off. But now what happens is that we have a Br minus from that Br2 piece, and we also have a Cl minus from the salt, because this is an ionic compound, right? It's a salt. It breaks up. There's an Na plus and a Cl minus. So now we have competing efforts here. Well, bromine can still go on. I mean, that's not a problem. Bromine can still go on here, but that is the minor product. So I want the major product, and the reason that that's the minor product is because there is a competing ion, and that is chlorine, and this is in a larger amount, just like water was, just like alcohol was, just like methylene chloride was, and everything. It's in a larger amount. We have more of it. So the Cl can actually beat out the bromine just due, again, to statistics. And this is a way that we can get two different halogens onto a compound. It doesn't have to be the same. So if you look at this, it's the only way that we know how to do this at this point. I've got bromine on one side and I've got chlorine on the other. All of the other cases so far have put two bromines on, two chlorines on. That was it. Then we did examples with a bromine chlorine and OH, or a bromine chlorine and a OR group for an ether. But now this is a way that we can get two different halogens onto a molecule. We can chlorinate it and we can brominate it if that's what we want to do. All right. To get this to flip, we could do Cl2 here. And if we do that, then the Cl gets added on first because that is the compound that we chose to use. So Cl goes there. And instead of NaCl, we could actually use NaBr here as well. It means the same thing. There's no difference. So we still have competing Brs and Cls that go on. And because Br is in a higher amount this time, because it's written on the arrow and we look at it as a solvent, then that Br will beat out that extra chlorine that is there. And we can get these things to flip depending on the order that we use as far as the reagents go. If I wanted to name this product, I could. This is propane. And it looks like halogens here, 1, 2, and 3. That will give me the lowest group number. So on carbon 1, I have a chloro. On carbon 2, I have a bromo. So B comes before C. So 2 bromo and 1 chloro, and propane will follow that. If I look up at the starting reagent, what do I name that? This is propene. And I can put a 1 there if I want to, because that's carbon number 1, carbon 2, and carbon 3. So 1-propene reacts with chlorine gas in the presence of sodium bromide, and we will end up getting 2-bromo, 1-chloropropane if that's what goes on. All right, so let's do some examples, right? You know me. I love examples. I keep saying it over and over because I want you to love them too. They feel left out, and they need love just like everything else does. So love them. And we'll do part A first. It says there are 2 nucleophiles in each of the following reactions. For each reaction, explain why there's a greater concentration of one nucleophile than the other, and what would be the major product. All right, so if I look at A, well, we do the same thing here, all right? And I'm just going to flip this to a clean screen so we can look at these one at a time, and I'm not scrunched up as far as space goes. So we've got CH2 double bond C with a CH3 that points up and a CH3 that goes over. And we're going to add, Cl2 with methanol. Okay, so there's our reaction. So the question really wants me to predict the product and then explain why we got the product that we did. All right, no big deal. So this is what we've been doing. So I'm going to take my starting reagent and I'm going to redraw it for my product side. And then I'm going to take my eraser and guess what? I'm going to break it. Two sides of attachment open up, one there, one there. So the Cl2 breaks apart first. The chlorine goes in first because this is what initiates the halogenation step. A cyclic chlorinated ion begins to happen. And then when that goes on, chlorine will behave like Markovnikov rule. So it looks at these two carbons and it says, I think I want to go here because I'm going to hang out with those hydrogens. I like those a little bit better. I'm a picky. And the molecule goes, okay, fine. We have a carbocation that gets formed at this point, and that carbocation is going to get the alcohol piece, which is the O and then the CH3. And folks, there's a product. That's all there is to it. That's what I need to do. Now the question says, why? Well, that's because this is a solvent, and there's a higher concentration of it, so it will beat out the chlorine that will be freed up in the halogenation step. And that's how we get our product here. All right, so we've just answered A. Now let's go on to B. B is CH2 double bond CH3, and we get two NAIs and an HBr. Oh, not really seeing this one, have we? This is a little weird. So I'm going to do what I've always done. I'll just redraw the starting reagent. So there we go. There it is. And then I'm going to double bond. And then I look at these things that are there. And I begin to question, what on earth is going to happen here? The two NAIs. These two NAIs... this is basically kind of like the salt that we have seen before in the past. This gives me Na plus and I minus, but there's going to be 2 times the amount because there's a coefficient in 2 in front. That's what that means. So double compared to everything else. And then this HBr stuff. So the whole point in this is to try to find an electrophile, okay? And in the other examples, it was Br2, Cl2. We don't really have that here. What we do have, though, is HBr. I know what HBr is going to do to a double bond, don't I? Yeah, I do. HBr is going to come in with a double bond. It's going to attack it, and 2 sides of attachment open up. And the H goes on first. That's the electrophile. And that's a very good electrophile for this reaction as well. H plays with other H's, so H will go here. Well, instead of writing it that way, CH2, I can turn that into a CH3, and that just cleans that molecule up a little bit. And now we get this carbocation that forms at that location. But now, normally, if it was just HBr, Br would be in there, and Br would come around, and it would attach to that spot. But the problem here is that I've also now mixed in double the amount with sodium iodide. So iodide is also there, and it's 2 times the amount that bromine is there. So we have another competition between the two. And, it's kind of like 2 friends going over the same person that they like. They're going to fight over them. Who can get them first? That's what bromine and iodine's going through right now. So bromine and iodine, look statistically, and you're going to see that iodine is going to be there in a larger amount. So iodine has larger chances of getting onto that molecule before bromine can. And folks, this is the product of this reaction. Now, bromine can go on. Bromine can go on in that spot, but that's a minor product. And the reason is because iodine is there It's just as good as bromine, really, in this case, and there's twice as much of iodine. So, folks, this is the proper reaction, and this is the product for this reaction. You got to keep in mind, HBr is going to initiate it. This is a reaction that we've seen before. We've already talked about the reaction of alkene and an acid like this. That initiates the reaction to go forward. And once that happens, a carbocation's formed, and now we can look at the I's or the BR's and think about which one will go on first. Okay? All right, next. CH3, CH, double bond, CH, CH3. We're going to add HCl, and this time, water. Okay. So very similar to what we've done before, I'm going to start with, guess what? Yeah, my reagent. There we go. Good news is it's pretty symmetrical. It's pretty even. So the double bond breaks. Two sides of attachment open up. One here and one there. And it looks like HCl is going to be added on. I know what HCl is going to do. All right, HCl is going to break apart the double bond, and H plays with other H's. Well, it doesn't really matter which one I put it on here. It's going to give me the same stuff. I'm just going to do the one to the left. So instead of CH, I can write a CH2 now there and just get rid of that one to clean it up. There's a bond that's freed up. That's a carbocation, and chlorine is there. Okay? But we also have water, and water is HOH. And water is regarded as a solvent here. That's why it's written on the arrow. So that water could compete with the chlorine. We could get chlorine that goes on there. That's not a problem. Whatever. No big deal. However, we could also get the OH from that water to show up there as well. Folks, there you go. There's going to be a product. One of the reasons is because water is such a solvent that this could form. This could happen. But let's go a little step further. HCl is by definition of acid. It frees up H+. We also have water that's a solvent. That H+ could actually get attached onto this molecule and form H3O+, and that is our hydronium ion. And this will leave me chlorine that is left behind. So there's a weird little thing that happens here, but we're going to keep it consistent. All right, we're going to go through the trends, but I do want you to know that the acid can release proton, and that proton can go to that organic molecule. When it goes to that organic molecule, normal steps happen. Double bond breaks, H adds on to the side that has the Makovnikov, whatever, everything else goes forward. But that hydrogen could also react with some of the water as well. And that hydrogen could generate H3O+, and then we get an acid and water, and then we can end up with a different type of product. All right, but we're going to keep it consistent, and we'll just keep the same trend going. There you go. All right, let's look at the next one. CH3, CH, double bond, CH, CH3, and this time we'll add HBr, and we'll add alcohol as a solvent. Well, just like before, you get the drift. I think you know how I think. You know how I work at this point. There we go. Double bond breaks, and then two sites of attachment open up. The HBr, the H makes it break. H plays with other H's. Doesn't really matter where it goes. I'll put it to the one on the left-hand side. And we could get BR that happens here. That's not a problem. That would be a product. Is it the major product? Maybe not. The reason it's not the major product is because I also have the alcohol that's there as well. That alcohol is a solvent. Statistically, it's there more, so I can get that particular piece that goes on at this point. But I get a mixture. I get a mixture of different products. And this is why, ladies and gentlemen, that when we do organic reactions in a lab, we really shoot for about 60%. 60% is actually good. In general chemistry, this would be unheard of. I mean, they would think that you're just an awful lab person if you give me data that's only 60% yield. I mean, where did the other 40% go? Down the sink? Weren't you paying attention? That's kind of what would go on in general chemistry class. However, organic, 60% is very good. I'm going to pat you on the back. You gave me really good data. And the reason is because all of these others that could form here, and you've got no control of it. I mean, no one is stopping that bromine from coming in and actually attaching. It might be there in a small amount, but no one's stopping it. It's just going to happen. There's nothing you can really do about it. So this is going to give me another product in addition to this one. And some of these reactions, there'll be tons of different ones. And if that's the case, my percent yield is going to go down, 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 because I have no control. I might be really good with my transfers. I might be really good with the steps of the reaction. But in the end, there's only so much that I can do as a lab person. And if I give you a 60% yield in organic, then we are excited. I mean, we are jumping up and down, and we are having a party in the lab, because very often that is unheard of as well. So that's where this video is going to stop. I think that I've confused you enough already with the halogens and those reactions that can take place. In the next one, we're going to talk about a different type of reaction, and it's going to be called oxymercuration reduction and alkoxymercuration reduction. I mean, try to say that 3 times fast. But this is the reaction that we're going to focus on next. You're going to see that the products from this reaction, though, are really no more complicated than the others. It's just a different type of reagents that we use in order to get there. We've got choices. It's a variety pack, and you need to appreciate that variety pack, because sometimes you get tired of eating the same old potato chips, and I don't want to give you the same potato chips every day in organic, so we've got to have the choices laid out on the table for us. And some days you might take a pack of Cheetos to lunch instead of some Lay's salty potato chips.